So today we're going to talk about section 14.4, and the topics we're covering are differentiability, linear approximations, and tangent planes, all for two variable functions. Our learning goals for today are going to be able to find a linearization of a two variable function and describe that linearization both graphically and algebraically. We're also going to find equations for tangent planes. We're going to define and apply local linearity. We're going to give criteria for differentiability. And finally, we're going to use the linear approximation method to estimate functional values. So let's start off by reviewing what we know about linearizations for single variable functions. Perhaps you don't remember this terminology, but I'm sure you're familiar with the topic. So let's say that we have some function f of x in the xy plane, and we want to approximate this function with a line at the point A. So when my x value is equal to A, my functional value is equal to f of A, and the point has coordinates A, comma, f of A. In order to create the linear approximation or the linearization of this function at the point A, f of A, which is the equation of this line, the tangent line, we already have a point. All we need is the slope of that line at that point where our x value is equal to A. And in this case, maybe I should label my axes. So we all know that the slope of that point is going to be the derivative evaluated at that point. So our slope is given by f prime of A. And that means that the linearization, if I decide to write this linearization in point-slope form, it means that our line in this case, maybe I should call my line L of x, that's this line, L of x, is given by our y value, which in this case is f of A, plus our slope, f prime of A, times x minus A. So this might look messy, but really this is just point-slope form, where this is the y-coordinate of the point, f prime of A is the slope, and A here is the x-coordinate of the point. And our only variable in this expression is the x in our L of x. So building on this, we're going to apply this to a linearization for a two-variable function. Watch this. I'll change this to a two-variable function. So instead of thinking about a curve in the xy plane, now we have to think about some sort of two-variable function. And I'm going to draw something that sort of looks like a sheet, because that's always what I draw for my two-variable functions. So now it's a function of both x and y, and I think of these as my outputs. And I'm going to talk about the linearization at the point A, B, f of AB. Because if I fix my x equal to A and my y equal to B, it means that the point in 3 space is going to have a z-coordinate given by my functional value, where my x is equal to A and my y is equal to B. So this point in 3-dimensional space is labeled A, B, f of AB. So I have a point. How can I linearize this two-variable function, though? A line isn't going to cut it anymore. I could think of having lots of lines that were tangent to this surface. A preview from our learning goals, we aren't going to use a line for this linearization. We're going to come up with a plane. So in this case, our linearization, we're going to think about a plane where we're describing it in terms of tangent lines given by our partial derivatives. So for example, I just drew a trace along this curve where x is fixed to some value and y is variable, and I'm thinking about what is the slope of this tangent line. Perhaps I should use different colors, that might make this clearer. And we know that the slope of this tangent line in this direction is going to be given with our partial of f with respect to y. So I'm going to write f sub y at AB is the slope of the tangent line where x is constant, and in this case exactly equal to a. Similarly, I can think of a different line. If I draw out a trace where my y is constant, where my y is equal to b, I can think of what is the slope of the tangent line in the opposite direction. And in this case, that's given by the partial with respect to x evaluated at the point AB. That's going to be the slope of the tangent line where y is equal to b. Using this information, we pull all of this together to come up with a formula for our linearization, and I'll go ahead and write that down. So our linearization, which is a plane, so it has two variables, our variables x and y, and in this case it's going to be equal to our z-coordinate f of AB plus our slope in the x direction, f sub x evaluated at AB times x minus our a coordinate plus f sub y evaluated at AB times y minus b. So what did we just do? This ends up being an equation for a plane. Why is this an equation for a plane, you ask? Let's break down each of the pieces. So this f of AB, just like our point slope form, this is exactly our z-coordinate of the point that we are taking this linearization at. So I'll label that as the z-coordinate. Our f sub x is the slope in the x direction. And direction. Our f sub y is our slope in the y direction. And then I'm subtracting out the x-coordinate of our point that we decided to fix our linearization at, and the y-coordinate of the point that we decided to fix our linearization at. All of these pieces together are exactly our formula for a linearization. One of the things that you might be asking is, well, I mean, this doesn't exactly look like what we had talked about before in terms of a normal vector fixed at a point. That's typically how we were describing what planes looked like before. The thing that I want to point out, well, is that these two things are equivalent. That's something actually that you can explore in your homework. We'll talk about why these two things are equivalent. And working from this, we can use this formula. This is exactly the formula of a plane, and that's what I'll write down next as a definition. I would write it below it, except that I'm out of space. So right above it, I'm going to write the fact that this equation is exactly the equation for our equation for the tangent plane at the point A, B, f of AB. So our linearization at the point AB is going to be exactly the equation for the tangent plane at the point AB, meaning that this linearization that we just found gives us this plane. Now that I'm adding more things, it's going to look even more awkward. And if I were to zoom in really close to this curvy surface, as I get closer and closer, because this is flat, it's going to get closer and closer to looking like a plane. There are a couple of criteria. If you have some sort of multivariable function that has cusps, essentially, the three-dimensional analog of a cusp, if it has pointy parts or jagged parts, then these linearizations aren't going to work out. And we're going to talk through some theory of technical criteria for when we can have linearizations or not. But before we get to that, let's look at an example of finding a tangent plane.